Hi guys, welcome to another tutorial. And today we're talking about integrals of polynomials. And as easy as they sound, polynomials are something that you've been familiar with for a long time. Integrating them, however, could be very challenging. Okay, so we'll start off from that point and we'll start to build motivation towards the two techniques that we're focusing today. Okay, and this is supposed to serve you as a motivation for trig sub, which is trigonometric substitution, and for partial fractions. We're going to call them in small form part frac. Okay, so partial fraction decomposition and trig substitution are two very important techniques that you need to learn in order to deal with polynomials. Okay, so let's start off with a very simple example. Let's say if you wanted to integrate this guy. So you have this expression in front of you. We're going to gradually complicate things, okay? So the first time we see this example, I'm pretty sure mostly everybody knows how to integrate this, okay? Because this is a very straightforward expression. All you got to do is split up the integral and, increase the power by 1 divided by the same thing. So if you use the power rule here, the integral of this guy is just going to be x cubed over 3 for the first term. And then it's going to be x squared and plus an x and plus a c. So easy peasy. So this is just like one way of integrating this very simple scenario. Now, when I talk about polynomials, there's one specific kind of polynomial we're going to be focusing on this time, okay? And that polynomial is the quadratic. Oops, the pencil just didn't want to work there. So quadratic expressions are very special, okay? The moment you think about a quadratic, the first thing that comes in your mind is to factor, right? You can factor a quadratic, you can find its zero, or you can kind of like see a parabola of a graph and all that stuff is going to come in your head. That's good. And that's the motivation we're looking for. Right now, what you see in front of you is a quadratic. Okay, so this equation was a quadratic, but there's multiple ways to write a quadratic, right? So when you saw the first kind of the standard way of doing that is to factor them, right? And if you eyeball this equation for a second, right, what you can see is that this could be easily factored out. And this integral could be equally written as like this. So the equation x squared plus 2x plus 1, this guy here, could be written in a factored form like this. The two factors here are supposed, just become x plus 1 and x plus 1. And you can write them as x plus 1 whole squared. So this is like in this form. So now if I give you an option to integrate this guy, right, there's going to be a little bit of tricks involved. Okay, you got to do a little bit of work here in order to do this. So I'll try to show you what it means. So in this case, you got to use u substitution. So you'll choose u to be x plus 1. And by the way, I need you guys to be very familiar with u substitution before we talk about any of this. Okay, so let's just begin then assume that you have enough knowledge about u substitution. So you pick u as x plus 1. This tells you that when you take the du, that's equals to dx. So now your new integral could be written as, the same thing could be written as u squared du. And this is a standard integral which you can compute, and that'll just be u cubed by 3 plus c. And when you substitute back what the u value was here from this expression, you get your integral to be, x plus 1 whole cube divided by 3 and a plus c. So now, well, if these two integrals were kind of same, right? This and that integral are kind of same, then these expressions should also somewhat be same. And in fact, they are, okay? If you expand the x plus 1 cube, you're going to get almost the same expression over there. So there shouldn't be any trouble. Now, one method, like the one method that you saw that, in this particular form was much easier to integrate. But when you have it in the other form, like in the factored form for an example, this took a while. You got to use the u substitution, you got to do all that work, and then you can jump back to the answer, right? So if I was to give you which method, like which way of solving the integral would you prefer out of the first and the second option, I think most of you guys will select this first one because it's easier to solve. Now, knowing that, that factored forms, sometimes kind of make it complicated for you to solve, can we try to think of a place where they could be actually useful? Okay, let's try to complicate this a bit. So if we go gradually to more complicated ones, the idea what I'm going to use here is, I'm not going to change the quadratic by much. I'm going to keep that the same equation here, but I'm going to slowly, move it into different forms. The two most prominent forms are going to be the one that I'm going to talk about. The first one is to just take that same quadratic, okay? So integral of x squared plus 2x plus 1 dx. But now instead of it just being in the integral, I'm going to put it inside a square root. Okay, a quadratic inside a square root is not a big deal if you look at it. But from integrals point of view, when you want to simplify this could give you, a lot of mess in your head, okay? This is kind of hard to integrate if you think about it that way. But however, we always know there are multiple forms you can write a quadratic in. So if I was to try to factor this to begin with, and we'll try to see the equivalent integral of this guy will just be x plus 1 whole squared square root, right? And now surprisingly this one is easier because you have a whole square of a square root, so this is nothing but the integral of x plus 1 dx, because the squares and the square root will cancel each other out, So now this becomes surprisingly easy, and you just go ahead and do, x squared plus 2 plus x plus c. That's the answer. So now you saw that before we started off, we were liking the non-factored form. But as soon as you get them complicated under some other operators like this, that's the first example. I'm going to show you one more, okay? The moment you complicate them like this, it's better to use the factored form, okay? Because you want to condense your expression in the smallest form, and you can, use any tools that you have in your head to apply that. So that was this complication. Let's do one more complication, okay? What if I wanna give you more motivation towards why the factor form is kind of sometimes easy to solve? I'll show you that. So the next form we're going to talk about is the same quadratic, okay? Not going to change that. Same thing, but now instead in denominator form. So when you have 1 over that quadratic, how do you even solve this thing? First time when you see that, it's not easy, again, because it would have been so nice if it was in nice factored form, but right even now, at this point, you don't even have a clue to where to begin, because right now we're just, stuck. But then again, the motivation is to, when you see a quadratic, try to see a factored form and see if that is kind of easy or not. Let's try to see. So if you convert this into factored form, you'll get dx over x plus 1 whole squared. So this looks kind of nice if you look at it. Comparing these two, the second one is going to be looking a little bit nicer. And then plus you have a nice linear inside a squared. So this is giving you hints about u substitution. So you can go ahead, you can choose u substitution and pick u as x plus 1. This will tell you that your du is just equals to dx. Knowing the fact, you can plug it back in and this integral becomes 1 over u squared du. And this could be easily solved by power rule, right? If you solve it, you get negative 1 over u plus c. And when you convert everything back into the u world, back into the x world, what you're going to do is negative 1 over x plus 1 plus c. And that's the answer. And it looks much easier now. So I hope at this point you're trying to see and you're getting the feeling that it's better sometimes to change a quadratic into a factored form. And that's what we're trying to, focus towards most of the time. And this is where, when you see right now, the equation that we considered was like a very nice and very easy one to factor out. How about if we take a little bit of complicated ones? Okay, so if we try to go ahead and make a complicated equation, which is going to be kind of hard to factor out, we know we'll run into trouble way faster than we're expecting it. Okay, so that's why we develop techniques here. At this point, I'm going to try to introduce a new technique. So what we've seen so far is the quadratics that could be factored out. So that could be factored, right? So that makes it easy. Good. What if you can't factor it? What if I give you a quadratic which is not easy to factor, which is like practically impossible to factor? How would you do that? So let's take an example there, right? So we covered already the factored forms. The other thing we can do is you can do the factor, then we can't. So let's do the one that you can't factor. You can't factor. So when you see equations you can't factor, one example is just, the same thing. If I change this guy, I'm going to change this very slightly. Instead of 1, I'm going to have a 2 now. The moment you add a 2, you are not going to be able to factor it. And it's evident because you can't think of two numbers that multiply to be 2 and add up to be 2 as well. Okay? And this is where you get stuck. So what do you do when you can't factor it? Something that you probably learned in high school was a method that it's kind of like shady right now, but I'm going to bring it back in. So if you can't factor, what you do is complete the squares. And this method is something that you guys learned before, but I'm going to give you a brief on that. So when you complete a square, what you want to do is you want to end up with a complete square, which means you want to convert this expression, somehow into a completed square. And I'll show you exactly how you can do that. So the motivation is to actually, first of all, rule of thumb, the way how I like to do it. This is not a perfect rule, okay? The way how I like to do it is I want to make sure, number one step, is make sure the x squared has a coefficient of 1. So let's say if this was like 5x squared for a second, right? What you want to do is you want to factor the 5 outside this expression and then do the inside part and then later on bring the 5 in, okay? You don't want to you don't want to mess it up there. Make sure the coefficient of x squared is 1. It's just my preference. There's multiple ways to do that. So if you know how to complete squares by yourself, you're good to go. I'm just giving you a brief overview of how I do it. Okay. So when you have x squared factored out with a coefficient of 1, that's nice. What you have to do is you have to write this expression like this. So this equivalent, I'm going to get rid of the 5. That's not there. This expression, this x squared plus 2x plus 2 should be written as an x squared plus 2 times x times something. Okay, I'm going to leave a blank there. And then I'm going to do the same blank squared minus same blank squared and a plus 2. So all I did is I inserted some stuff right here in the middle. Okay, the plus 2 stays there. This whole expression is just trying to complete the square. And I'll show you exactly what I mean. When you have an x squared plus 2x times something, what you want to do is if these equations are equivalent, the terms with the x coefficient should be equal on both sides, right? So in this case, this term on the x is 2x. In this case, we already have a 2x. So what number should come here in order to match this equation with the 2x here? Okay. And if you think about it, that number should be 1. Okay. And that should be 1. Once you have a 1 there, whatever comes in that blank goes in this blank, goes in this blank. And what happens is automatically this form is a complete square. The complete square is x plus 1 whole squared. And if you resolve this remaining portion, that's negative 1 plus 2, which is equals to, just like 1. So, plus 1. Now we have another form. I'm going to show you that. So, x squared plus 2x plus 2 could be written like x plus 1 whole squared and a plus 1. Okay, some people might have thought it's just easier to, kind of like eyeball it in your head. So there are multiple ways to do completing squares. It's completely up to you. You can watch video tutorials online about how to complete squares and stuff. Some people also call it converting the parabola in a vertex form because this is kind of the vertex form, right? But completing squares, vertex form is exactly the same thing as long as when you can end up with this expression here. Okay, when you end up with this expression, let's try to see what our integral becomes, right? So if this problem was given like in 1 over x squared plus 2x plus 2, this integral would now look like, because you can't factor it, so you have to complete squares. Well, it's a little bit better, but it's not as, as nice it would have been if you had just one single factor at the bottom, right? So now when you have things like this, when you have completed square form, it's going to be kind of hard to, go to the next step, because the motivation is still to make this whole thing at the bottom into one single term. Okay, we want to make that. So in order to do that, what we do is we use help of trigonometry. Okay, so this is going to give you motivation towards trig substitution. I'll show you exactly how to use them, right? But here we're trying to bring in the context. When you can't factor things, you have to complete squares and use trig substitution. But when you can factor them, it should be easy to do. And there's sometimes a technique called partial fractions. So now we're going to draw the bigger picture, and then we're going to learn the methods of doing this. The bigger picture is when you see a quadratic, okay, in 3 basic forms. The basic forms are in square root, or 1 over, or, like in the other case, combination of both. So when you see a square root, or 1 over that, or you have 1 over square root of that. Okay, so any kind of this thing. Whenever you see a quadratic in this scenario, what you should ask yourself is 2 things. Can you factor? So if you can factor it, and if you can't factor it, then you will have to complete the square. Okay, it's either going to be one of those. So if you can factor it, the method you're going to use is method of partial fractions. And when you can't, you got to use method of trig substitution. And that's it. That's the way you will start off your argument, at least to determine what techniques you're going to use for certain things. So let's do quick examples here, right? So if you think about it here, if I give you a quadratic for an example, I give you a quadratic like this. So when you see this expression, you got to ask yourself, this is a quadratic inside a denominator, okay? So it's better to work with either the factor form or the completed square form, right? Which one do you think is better here? The first line of defense is going to be try to factor it first, right? So if you try to factor it, what do you expect? Is it going to be factorable or not? Let's try to see. So we're looking for 2 numbers that multiply to be 2, but add up to be 3. And yes, this could be easily factored out. This could be easily factored out into this. So you have x plus 2, and you have x plus 1. So you got 2 factors like this. The moment you can factor it, you know the method that you got to use is partial fractions. Okay, I'll show you exactly how to solve it in a bit. But right now we're trying to find and identify which method we're going to use, okay? So that's one example. Let's do another one. Let's say I give you this equation. What you have right now is something that's already factored. It is a quadratic though. When you expand it, it's going to be x squared plus 2x, right? But because it's already factored, you should just, hands up, go start with partial fraction. Because it's already factored. Okay, now let's try to do one more example. So now we're looking for whether we can actually factor this out or not, right? So let's try to see. In this case, when you can try to do is, you have an x squared plus 4x plus 8. Two numbers that multiply to be 8 but add up to be 4. So factors of 8 are just going to be, 4 and 2. So there are no ways you can factor this. So if it's not being able to factor, you have to do the other way. You have to complete the squares, right? Which you can do that easily. I'll show you exactly how to do it. And then what you have to get is to use the method of trig substitution. Okay, if you want to complete the squares of this guy, let's take it down here and try to see that. 4x plus 8. So the method is to write, first of all, check the coefficient of x squared is 1 or not. It is 1, so we can go ahead. You have to write the expression like x squared plus 2x something plus that thing squared minus that thing squared and a plus 8. That's the template. So when you put the template, all you got to do is match up this term with this term. So what number do you think should go here for us to make this whole term into 4x? And if you can see, it's already there. So you got to make sure you have a 2 there so that this will become a 4x. So that 2 will be here too, 2 will be here as well. So when you see this whole portion is a whole squared of x plus 2, right? And then this could be resolved into minus 4 plus 8, which is equals to plus 4. So plus 4. This form in the completed square could be written as x plus 2 whole squared plus 4. And that's nice. It's going to be a slightly easier way to look at it, but not the best. Ideal case would be to factor it out, because then partial fraction method is a slightly easier method than trig substitution. But so far so good. If you get that trouble, you can at least work your way around it, right? So that's this. And that concludes the scope of this motivation, right? So now I'm going to be talking about, just the method as partial fractions and method of trig substitution, okay? All of them in like one separate pieces. So let's look at the other video and I'll catch you back in the partial fraction expressions and trig substitution.